Hi students, good morning. Today we are going to discuss about a new chapter that is biomolecule. We have already discussed about phenol, alcohol and others. Today we are going to discuss about biomolecules. Let us see biomolecules. So in biomolecules, this is chapter 14, biomolecules. And let us see what is a biomolecule. What is a biomolecule? It's a molecule, organic molecule, which is made by living organism. So that is called a bio. From bio, we know that it is connected with living. Okay, so organic molecule made by living organism is called a biomolecule. It's mainly consists of what? Carbon, hydrogen, and oxygen. Okay. Now, there are different classes of biomolecules: carbohydrates, proteins, nucleic acid, lipids. All of these are coming under biomolecules. So today we are going to discuss about the first class, that is called carbohydrates. Carbohydrates, we know that it is present in all pulses. Okay. So what is the definition of a carbohydrate? These are broadly defined as, what is it? It is a polyhydroxy. What do you mean by polyhydroxy? Polyhydroxy means it consists of more than one OH group. Okay. So it is polyhydroxy aldehyde. So in this carbohydrate, it consists of carbon, hydrogen, and oxygen. So it consists of hydrogen and oxygen. How it is present? It is consist of it is present as OH functional group, that is polyhydroxy. More than one OH group will be there. And aldehyde group also will be present. CHO or C double bond OH group is also present along with the, or either an aldehyde group or a ketone group must be present. So carbohydrates are what is carbohydrates? They are termed as polyhydroxyaldehyde or ketone and their derivatives, or a substance that yield one of these compound. Okay. So if it is not a polyhydroxyaldehyde or ketone, if it undergo hydrolysis, at least it will give some of these compounds. Okay. So it is, so what is carbohydrates? From the name itself, we can understand that it consists of carbon, hydrogen, and oxygen. And the functional group present is hydroxyl group and ketone or aldehyde group. And it is named as O's. Okay. Named using O's, fructose, glucose. Okay. These are example. Okay. Now let us see some other important facts about the carbohydrates. Its empirical formula will be always CH2O. For example, C6H12O6 is an example. This is a OS. OS means it is a glucose. It is a carbohydrate. So this, if you are taking the common factor 6 and divide every numbers, we are going to get what? CH2O. So this is the empirical formula of glucose, right? So carbohydrates are having the empirical formula CH2O. Carbohydrates means hydrates of carbon. It is a hydrate of carbon. And the most abundant carbohydrate is what? Glucose. And carbohydrates are polyhydroxy. Already we discussed polyhydroxy, aldehyde, and ketone. Okay. Now let us see some exceptional case, a general formula of carbohydrates. What is the general formula of carbohydrate? Carbohydrate may be, the general formula of carbohydrate is, the general formula of carbohydrate is CxH2OY. Okay, CxH2OY. Okay. So always it is not applicable. There are some exceptional cases also. Okay. Now let us see. It consists of carbon, hydrogen, and oxygen, we know, and its general formula is CxH2OY. Okay. Now we are going to see that. So there are some exceptional cases also. Actually, glucose, we know that it is a carbohydrate. So that is C6H12O6, right? This is glucose. So this can be written as CxH2O6 times. Okay. That is, it is the same form as CxH2. CXH2OY. In this form, we can write it, right? But there are acetic acid also. If you are taking acetic acid, you can write it as C2H2O 2 times, but it is not considered as a carbohydrate. It is not a carbohydrate. Even then, it is existing in this particular general formula. So this is an exceptional case. And if you take C6H12O5, it is actually a carbohydrate, but we cannot write it in this form. Okay. So there are few exception cases, but generally we can tell it's a general formula is CXH2O Y times. Okay. Now, what are carbohydrates are also called as saccharides. What is the meaning of that? That means sugar. Okay. Some of the carbohydrates are sweet in taste and they are called what? Sugars. If the carbohydrate is sweet, then it is called a sugar. We know that in our home, which sugar we are using? We are using sucrose. Okay, it is very sweet. Okay, also milk consists of a particular sugar that is called a lactose. Look at this, it is ending with the O's. Okay, O's. So now let us see the classification of carbohydrates. Okay, so carbohydrates we can classify as monosaccharides, disaccharides, oligosaccharides, and polysaccharides. Okay, so based on what? Based on their behavior on hydrolysis. So carbohydrates, these monohydrates, only one single molecule is there. We cannot undergo any sort of hydrolysis on this. Okay, it is not going to split. Okay, so that is monosaccharides. Glucose, fructose, galactose are example for monosaccharides. Disaccharides on hydrolysis, you are going to get sucrose, you are going to get 2 sugar units. Okay, here it is only 1 sugar unit and we cannot hydrolyze it. But in disaccharide, if you are hydrolyzing it, you will get 2 sugar units again. Okay, after hydrolysis. So sucrose, lactose, and maltose are example. Oligosaccharides 2 or 10 or more than 2. Here in this tab, in this book, we are classifying oligosaccharides from 2 to 10 sugar molecules. So disaccharide is included here in oligosaccharides. Okay. So oligosaccharides 2 to 10 sugar molecule. Example are raffinose and stachyose. Okay. Now polysaccharides, saccharose. Okay. Polysaccharides means that consist of more than 10. Okay. 10 or more sugar unit on hydrolysis. If you are getting, that is called a polysaccharide. Starch, glycogen, and cellulose are example for that. Okay. Now let us see monosaccharide alone. So first category, we know that it is a single unit. It is not going to hydrolyze. That is called a monosaccharide. So example for monosaccharide is glucose, fructose, and galactose. So it is not going to undergo any sort of hydrolysis. Now, about 20 monosaccharides are known to occur in nature. Okay. So now next is definition of monosaccharide. What is monosaccharide? It's a simple sugar that constitute the building block of more complex form of sugar. So oligosaccharides and polysaccharides are made up of monosaccharide. The monomer present in all of this, or the simple unit present in oligosaccharides and polysaccharides, are actually what? Monosaccharides. Okay. Now monosaccharides are further classified into 2 based on the functional group present in them. So if the functional group present in a monosaccharide is aldehyde, C double bond or H, then it is called aldose. If the functional group present in a monosaccharide is a ketone group, then it is called a ketose. That is the classification based on what? Based on the functional group. Okay. Now let us see. The number of carbon atom constitute the monosaccharide is also introduced in the name as in evident from the exam. So based on the number of carbon atom present, we can name it. Okay. Let us name them. So in the monosaccharide, if there is only 3 carbon atom, then it is named as triose. Okay, if it consists of an aldehyde, then it is called aldotriose. If it consists of a ketone, then ketotriose. If it has 4 carbon atom, then tetrose. If there is 5 carbon atom, pentose, 6. But based on the aldehyde or ketone present, its name again will change. If it is an aldehyde, aldotetrose. If it is a ketone, ketotetrose. In this way, the name will be changing. Okay. Now, what is oligosaccharide? We already discussed the carbohydrate which yield more than 2 or 10, 2 to 10 sugar units on hydrolysis. That is called oligosaccharides. The classification of oligosaccharides are here. Disaccharide, maltose. On hydrolysis, it will give you glucose, 2 glucose unit. If it is lactose, 1 glucose and 1 galactose you will be getting. If it is lactose, you will be getting 1 glucose and a fructose. Okay. So trisaccharide example is raffinose, glucose, fructose, and galactose you will be getting on hydrolysis. Tetrasaccharide is stachyose. When you undergo the hydrolysis, you will be going to get galactose, glucose, and fructose. 2 galactose will be there. Okay. Now pentasaccharides means 3 galactose, glucose, fructose. Means on hydrolysis, you will be getting 5 monosaccharides units. Okay. Now, what is polysaccharide? Carbohydrate which yield a large number of monosaccharide, means more than 10 or more sugar unit on hydrolysis. That is called a polysaccharides. Okay, so polysaccharides are carbohydrates molecule which are made up of long chain of monosaccharide. Lot of monosaccharide will be there. Example for that is starch, cellulose. Starch is present in our body. We know that food is stored in the form of starch, and cellulose is present in plants. Glycogen, gums, all these are examples. Okay. Now, what is non-sugar? Already we learned what is sugar, which is having a sweet taste is called a carbohydrate, which is having a sweet taste is called a sugar. Non-sugar means which is not having a particular sweet taste. Then it is called a non-sugar. Okay. Now, classification of carbohydrate in terms of taste. That is what we done now, sugar and non-sugar. So sugar example sucrose and glucose. Non-sugar example is starch and cellulose. Okay. Now next classification based on reducing group. Okay. If the carbohydrate will reduce the Fehling solution and tolerance reagent, then it is called are referred to as reducing sugar. Okay. So into the carbohydrate, if you are pouring Fehling solution and tolerance reagent, if it reduce Fehling solution and tolerance reagent, then it is called a reducing sugar. All monosaccharides, whether aldose or ketose, they are all reduced because they are CHO group, aldehyde group and keto group are free. So all monosaccharides are reducing sugar. They will reduce Fehling solution and tolerance reagent. Okay. But carbohydrate which cannot reduce the Fehling solution or tolerance reagent are referred to as reducing sugar. Okay. Non-reducing sugars, not reducing, non-reducing. Okay. Now we can learn about a monosaccharide. Example for a monosaccharide is glucose. How we will prepare glucose? Let us see first how we will prepare the glucose. When you treat an acid, okay, this is where if a sucrose is boiled with dilute hydrochloric acid or sulfuric acid in an alcoholic medium solution. So dilute, boil, you have to boil, and we have to use dilute HCl or H2SO4, and in an alcoholic medium we are using it, then we are getting glucose and fructose. So sucrose will split into 2 monosaccharide unit, which are the monosaccharide glucose and fructose. So this we can use for the preparation of fructose and also for the preparation of glucose. Okay. And or if starch or cellulose, okay, is hydrolyzed with a dilute sulfuric acid, boiled, you have to boil it, then we will get n number of glucose. A lot of glucose we will be. Starch and cellulose, the unit present, the small unit present in them is glucose. So it will undergo hydrolysis and we will get n number of glucose. Okay. Now let us learn the structure of glucose. Before that, we can understand what is a glucose. Glucose is an aldohexose. Aldohexose. From the name itself, we can understand that aldo means it consists of an aldehyde group. Hexose means it consists of 6 carbon atom. Okay. It's a monomer of many of the larger carbohydrate, namely starch and cellulose. It is the most abundant organic compound on earth. The most abundant organic compound on earth is glucose. Okay. So now we are going to see the structure of glucose. We know already what is the formula, that is 6H12O6. But there must be some evidence to understand the structure of glucose. So what are the evidence to understand the structure of glucose? So this is very important part. First, what we have to write, this is a molecular formula. We only know the molecular formula and about what is the functional group, not about what is the different hydroxide group where it is present. Nothing we have no idea about that. So we are going to do some experiment. From that we are getting the proof that where and where this hydroxide and aldehyde groups are present. Okay. So when glucose is treating with hydrogen iodide, okay, when you are heating, you are getting normal hexanes. From this, what evidence we are getting is 1, 2, 3, 4, 5, 6. 6 carbon atom is arranged like this. Okay. 6 carbon atom are linked in a straight line. That idea we are getting. 6 carbon atom are linked in a straight line. In order to get that idea, you have to treat it with hydrogen iodide. Then you are getting normal hexane. From that we can understand no branches, nothing is there. 6 carbon atom is arranged in a straight line. Okay. Next, you are treating it with the NH4OH. So C double bond OH is treating with the NH4OH. Okay. So when you treat it with the NH4OH, what will happen? Here, these two react together. C double bond OH and NH4OH react together, and we are going to get what glucose react with the hydroxylamines to form an oxime. You are going to get an oxime. This is an oxime we are going to get. At the same time, if you are treating the C double bond OH with HCN, HCN means H plus CN minus, right? If you are treating, this will be shifting to this become negative, this become positive. CN will be coming and joining here, and H will be joining here. So you are going to get this compound, SEH, CN, CNOH. Okay, this is called a cyanohydrin. Okay, so you're going to get a cyanohydrin. And here also you are going to get a CH double bond NOH. So actually how that reaction is taking place, let us see. The C double bond OH is going to react. Hydroxylamines means NH2OH. So H2NOH, NH2OH, right? So this H2O will be removing, and this bond will form like this, CH double bond NOH we are getting. So this is reacting, NH4OH and HCN is reacting with an aldehyde group there. That is why we are getting this product. Okay, so we can understand that an aldehyde group is present from this. So what idea we got? There is a C double bond O group, not particularly aldehyde. We can tell that C the carbonyl group is present. So here we got that it is a straight line, straight chain, and it consists of C double bond or group. We understood from this particular reaction. So if you are treating it with the bromine, mild oxidizing agent, bromine is a mild oxidizing agent. Aldehyde will undergo oxidation even with a mild oxidizing agent. So ketone will not undergo. So from that, we understood that it is undergoing oxidation by mild oxidizing agent and converting into corresponding carboxylic group. So from that, we understood that the C double bond of present is actually what? An aldehyde group. So from here we got an idea that there is C double bond O, and from here, from the oxidation using mild oxidizing agent, we understood that the C double bond O present is actually aldehyde. Okay. Now you treat it with acetic anhydride and you are getting penta-acetate. Okay, after the reaction we are getting a glucose penta-acetate. So from that what we understand is, okay, everywhere we are getting OC double by Stirling gauge. So OH is reacting with the acetic anhydride. We learned in previous chapter OH group will react with acetic anhydride, and we will get the corresponding ester. So 5 we are getting means 5 OH group is present here. That idea we got here, that is 5 OH group is present in a glucose. Okay. Now, about the structure, we still want to study more. So now the aldehyde undergo oxidation with nitric acid. So when it undergo oxidation, we can see that both the end, we are getting COOH, that is saccharic acid. Okay. Also, if gluconic acid means it is having COH group already at one position, other position we have a primary alcohol. So a primary alcohol will undergo oxidation with the nitric acid and we will get the corresponding COH. Okay. So here CHO, even mild oxidizing acid is needed to convert into COH. Even a primary alcoholic group is present. That is why this part also undergo oxidation reaction and we got COH. Okay. How we confirmed it is a primary alcoholic group? Because gluconic acid also contain a primary alcoholic group. When it is reacting with the nitric acid, we are getting corresponding COH. So from that we understand that the primary alcoholic group is also present in a glucose. And after all these, we understand that what all idea we got a lot of idea that it consists of a CHO group, it consists of a primary alcohol group, and it has 5 OH group. All this idea we got from all these experiment, and we confirmed that actually the structure, its configuration correctly represented as 1. This is the configuration of glucose. Okay. And from all the idea, from all these 6 experiments, we understood that actually the structure of glucose is like this. How it is: CH2OH here down, and after that 1 H here, 1 OH here. So next also same, like 1 OH here, 1 H here. Now there is a flipping here, that is 1 H here and 1 OH here. Okay. And after that same way we are writing C1 H here, 1 OH here, and CHO. So this is the structure of glucose. From all this evidence, we understand that structure of glucose is this. The structure of gluconic acid is like saccharic acid, and gluconic acid also we found it is like gluconic acid is this, and the structure of saccharic acid is this. Okay. So we actually need the structure of yes, glucose only. So this is the structure of glucose. Now, how we will name it? Actually, glucose is a dextrorotatory, so we will assign plus to this. Okay. So this is plus glucose. Glucose is always plus. It is not like L or it is D. Okay. Small letter D or a plus indicate the rotation. Okay. Rotation in a optically active light, in which direction it will, sorry, a plain polarized light, in which direction it will be rotating. Okay. When it is passing through this glucose solution. So when a plain polarized light is passing through this glucose solution, it will rotate the plane of the polarized light to right. It is dextrorotatory. That is why it is indicated using plus sign. Okay. Or we will sometime indicate using D. Okay. There is no relationship between D and a plus. So how we will assign a config? D is the configuration and plus will indicate the optical rotation. Okay. So how we will explain D? What is the configuration? So there is an easy way to find out the configuration also. How we are finding out the configuration? Actually, we are comparing glyceraldehyde. Okay. Actually, this glyceraldehyde we are taking as a reference compound to assign the configuration. So in this glyceraldehyde, OH is on the right side, so this is considered as D-glyceraldehyde. If OH is on the left side, that is considered as what? That is considered as a L-glyceraldehyde. In this way, we are finding the configuration. So configuration and optical rotation is 2 different things. Okay. So there is no relation between optical rotation and configuration. So configuration, how we are assigning? Configuration we are assigning by comparing it with the glyceraldehyde configuration. So if OH is on the right side, that is D, and OH is on the left side, that is called the L configuration. So here also we can see in the glucose, if you are taking glucose is D, because if you take this part, only this part, That is glyceraldehyde configuration, right? This part, if you are taking, if the OH group is on the right side, then it is assigned as this. So the glucose is D configuration, and it is having plus sign because it's optical rotation, that is dextrorotatory. Okay, so D or L indicates what? Configuration, and plus or minus indicate optical rotation. Okay, so D and L configuration we are finding using glyceraldehyde configuration. Plus or minus, we will see the optical rotation, whether it is dextrorotatory or levorotatory, and we are assigning this. Okay. Okay. Now, so we understand what is the configuration of glucose also, that is D-glucose. That also we understand. Now, there are some cases, because already we know that there is an aldehyde group present in it, but some of the reactions of aldehyde we are not getting. Okay, when it is treating with the Schiff's test, undergoing Schiff's test, it does not form hydrogen sulfide addition product with NaHCO3, and also it will not give a Schiff's test. So this is actually the characteristic test for what? Aldehyde and aldehyde. So it is not giving that. Also, the hydroxylamine, the pentaacetate of glucose does not react with the hydroxylamine. So these three exception cases we have seen. Even if the aldehyde group is present, it is not undergoing these two tests. Okay, so what will be the reason for that? We found out at last. What is the reason? Actually, the aldehyde in the, what is the structure of glucose? Glucose is like this: CH2OH, CHOH, CHOH, and then there is a flipping, that is H here, OH here, and then COH, H, and then C double bond OH. Okay, so actually the first, this is the first position, right? First, and this second, third, fourth, fifth. Okay, and in these two position, what is actually happening here? This OH group and this O group is fusing together, water is eliminating and forming a ring. Okay, so the first, this is the first position, second, third, fourth, fifth position. This OH and COH group, C double bond OH group, are fusing together. Okay, and what is eliminated and what we are getting? We are getting CHOH here. O is going to fuse between them. Okay, so this is what happening in the case of glucose. So sometimes our C double bond or H group is not available. That is why this is not giving this Schiff's reagent test and hydrogen sulfide addition test and hydroxylamine test, because this C double bond O present here, that is C double bond OH group present here, is fusing with the OH group present in the fifth position, and there is a ring formation. So how many carbon atom in the ring? 1, 2, 3, 4, 5 carbon atom and 1 oxygen. That is, it is as forming a 6-membered ring. Okay, 6-membered ring. So we done so many studies and we found that there are two forms. Okay, when it is forming, we are getting actually alpha form and beta form. This part is same only, D plus glucose, D plus glucose. So what is the difference in alpha and beta form? In alpha form, the first position, the OH group is on the right side, and in the beta form, the first position, the OH group is on the left side. That is the difference. Okay, so in alpha form, OH group is on the right side, and beta form, OH group is on the left side. If this difference in OH group produces two isomers here, so they are called anomers. Okay, they are called a different name, anomers. Okay, and this carbon is called a anomeric. The first position, the carbon is called a anomeric carbon also. Okay, and how we are getting these two forms, that is important. The alpha form is getting how? By the crystallization from a concentrated solution of glucose at 303 Kelvin. At 303 Kelvin, a concentrated solution of glucose undergo crystallization. We are getting this alpha form. And if you are taking hot saturated solution of glucose and at actually 371 Kelvin, if it is undergoing crystallization, we are getting beta form. So this is the case, different temperature and different condition, we are going to get alpha form, and these two anomeric forms are getting at two different temperatures upon crystallization, and their melting point is also different. Alpha form is having 419 Kelvin, and the temperature of a beta form is actually 423 Kelvin. Okay, so there is difference in the temperature, difference in the formation, difference in the OH group. Okay, so if the carbon is called anomeric carbon because on the first carbon, because of the flipping of the OH group, we are getting two anomeric form. Okay, so actually this glucose is existing in a 6-membered ring. Okay, 6-membered ring consisting of oxygen. So this is actually called a pyran. So the structure of glucose will resemble pyran. So it is called a pyrano structure. So that is pyrano structure that is put forward by Haworth, and it is called Haworth structure also. So how we will write pyrano structure? So that is the structure which resemble pyran. Okay. So first I will show you these two structure, how to draw alpha form and beta form. So alpha form, how we will be writing? CH2OH. Yes. And after that one CH is there, and here one O will come. And then next we know that OHH. And next we have CHOH. And next we have COHH. And after that we have OH on the right side if it is alpha, and H on this side, and it is fusing with this oxygen. So this structure, how we will represent in this form? So first you have to draw oxygen atom like this. This is a 6-membered ring, and here we are putting oxygen atom. Okay, and the first we will start from here. 1, 2, 3, 4, 5. Okay, 1, 2, 3, 4, 5. See, up to 5th carbon, we will be writing it like this. So which is your first carbon? This is your first carbon. Okay, and this is your first carbon, and your first carbon, those which is written on the left side will be up. Okay, so H, OH. So here also those which is in the second carbon, look at hydrogen is on the left will be up. So H, OH. Again, third one, how we will write third one? OH up, H down. Again, fourth one, H up, H is on the left, so H up, OH down. And here always CH2OH will be up. That is our 6th carbon. Okay, so 6th carbon will be always up. In every form, CH2OH should be always up. So this is the representation. So if you want to represent the alpha form, how we will represent? The OH will be here and H will be here. That is the only difference of a beta form, right? This was alpha form. So we will draw like this. Okay, oxygen atom here, we will draw like this. And after that, what we are writing? First, second, third, fourth, fifth. So first carbon, we can start from here, right? This is first. So where is H? Up. Right side, OH on the left side. So left should be always up. So OH, H. Okay. Next carbon, H on H, OH. So third carbon, OH up, H down. Next, left side H. So H up, OH down. And then fifth carbon, always I said CH2OH should be up and H should be down. In this way, we'll be representing the, this is the Haworth structure. So those which is written on the left side, we will be representing up, and those which is writing on the, those which is present on the right side, we will be writing down, and CH2OH should be always up. Okay, so we will be starting the first carbon from here. Okay, in this way, we will write the pyrano structure. Okay, now this is all about glucose. Now let us see the other monosaccharide. So what is the other monosaccharide? That is called a fructose. Fructose is also obtained. We already discussed about the preparation of glucose and fructose. Now, what is special about fructose? Fructose also has the same molecular formula. So fructose is actually an isomer of glucose, but its structure is different. Okay. And it is actually that glucose, we learned that glucose is aldohexose, but this is not aldohexose. This is ketohexose. Okay, this is having a keto group. Okay, it consists of a ketonic functional group. Okay, and it is also D series, but it is minus. Minus means it is levorotatory. In the its optical activity is different. It will shift the plane of the polarized light to the left, not to the right. So it is having D configuration similar, same molecular formula similar, but it is having a ketonic group and it is L form. Okay. So let us see the how its structure is. Some more factor about fructose. Fructose is an important ketohexose, already we discussed. It is obtained along with the glucose that we learned. It is natural monosaccharide. It is present in honey, vegetables, fruits, and all. It's a pure form. It is used as sweetener also. So next, let us see the open structure of this fructose. So how it is, look at this CH2OH, and just like glucose, our OH group, the first two OH groups on the same right side, okay, and after that there is a flipping, just like in glucose, H here, OH here, and after that there is C double bond, keto group, and then CH2OH group, okay. So this is the open structure of, so we can see this is D-glucose because it is OH group is on the right side, resembling D configuration. So this is D-fructose, okay. It is resembling D-glyceraldehyde, right? We are referring with the D-glyceraldehyde. Now let us see the closed structure also. Actually, just like how in the glucose, the CHO group is fusing. Here also fusing is there. So fusing is taking place here. Okay, in the second carbon. We know that second carbon, actually what is the structure? CH2OH, COHH, COHH, then CHOH, and then C double bond O, then CH2OH. This is the structure, right? So this keto group, their aldehyde group was fusing. This keto group will fuse with this OH, and we are getting a structure. But the member is not. It is not a 6-membered ring. Actually, it is having how many member? 1, 2, 3, 4, 5-membered ring we are getting. So it is not resembling pyran, it is resembling furan. Okay, furan is a 5-membered ring with one oxygen atom. So it will be resembling a furan. Okay, so because this CH2OH is not included there. Okay, that is the reason. So how we will write is when it is fused, we will get two structures. So CH2OH that is present here, we will be writing here the first carbon. Okay. And this is the two structure. We will get here also alpha and beta form. If OH group is present on this side, then it is called a alpha form. If OH group is on the other side, left side, then it is called a beta form. And this is fructofuranose. Furanose means it will resemble that was glucose was pyranose, and this is furanose because it is resembled furan. Okay, now how we will write this furanose form? First, we have to draw the furan here. Okay, and we are considering this position as a second position. Okay, second, third, fourth, fifth. So where is our first CH2OH? That is here. Okay, left side means it will be coming up. This is our first CH2OH, then OH down. Okay, and after that again our OH group on the right side, left side. So OH up, H down, and then next is H, right? H on the left side. So H up, OH down, and again here CH2OH. I said this 6 CH2OH always will be up, CH2OH and H. Okay, So this is a 6 CH2OH. In the other structure, what is the only difference? This OH will be coming up and this will be coming down. That is the only difference. Okay. That's all for today. Thank you.